Okay, section 18.4, entropy changes in the universe. So thus far, what we've done is calculations involving entropy changes for the system, for the chemical reaction. But recall that chemical reactions are often associated with changes in energy, enthalpy changes, to the surroundings, right? An exothermic reaction releases heat to the surroundings. An endothermic reaction absorbs heat from the surroundings. So it's useful for us as we discuss entropy changes to consider that entropy changes can occur in two different regions: the system and in the surroundings, both of those. And so we're going to make the following claim. If the change in the entropy of the system plus the surroundings, right, the two of them together, is greater than 0, then the process that we're studying is spontaneous. And if the change in entropy of the system plus the surroundings is less than 0, it's negative, then the process is non-spontaneous. Okay? So this leads us into our approach for determining whether a process is spontaneous or not. So for example, imagine you have a chemical explosive and you detonate it. It will explode and it will release molecules into the environment, into the surroundings, right? The explosive is essentially the system. And the explosive, as it releases molecules and atoms and energy into the surroundings, the entropy of the system is going to change. But the entropy of the surroundings is going to change as well. As heat is transferred to the surroundings, thermal motion will change in the surroundings. The molecules in the surroundings will increase in temperature, increasing their entropy. So what we're going to do is we're going to write it this way. This is the notation we'll use with your textbook. Delta S of the universe, meaning the system plus the surroundings, is going to be equal to delta S of the system, that's the chemical reaction for most of our purposes, plus delta S of the surroundings. And if delta S of the universe is greater than 0, then the process is spontaneous. If delta S of the universe is less than 0, then it's non-spontaneous. And this gives us an approach for predicting. Remember, science is about predicting. We want to be able to predict whether something is spontaneous or not. What this says is if we can somehow determine these two quantities and then add them together, we can answer that question. Now, we've already learned how to do this part, right? We already know how to find the change in the entropy of a system. The question then is, how do we find the change in entropy of the surroundings? And the clue to the answering that question has to do with enthalpy. So when we think about entropy, what affects entropy? Heat affects entropy. So for example, if I have atoms or molecules at low temperature, and I suddenly put heat in, transfer energy, right? Energy in the form of heat. what happens is those molecules now have extra energy. They have a greater amount, so this is now higher T, so high temperature. They now have a greater amount of entropy. Their entropy is increased by adding the energy to those molecules. So that's the clue. How do we add energy? Well, in our previous discussions, in General Chemistry 1, and in kinetics, and in some sense chemical equilibrium, what we've learned is that one way to increase energy, or to add energy or remove energy, is enthalpy. So, in other words, if you have an exothermic reaction, what's an example of an exothermic reaction? Combustion. Combustion is an exothermic reaction. It releases heat, transfers heat to the surroundings, right? Here, heat goes into the surroundings. Or maybe we'll say out to the surroundings if we're looking from the perspective of the system. So that means the entropy of the surroundings is going to change. So that's the key. So here's the mathematical relationship. The change in entropy of the surroundings is equal to the negative of the change in enthalpy, heat, of the system, but it also depends on temperature. At higher temperatures, the change is not as big. At lower temperatures, the change is bigger. So if you have a low temperature with a given amount of enthalpy change, that will affect the entropy change of the surroundings to a much greater degree than if you're at higher temperature. T is a large value there. Now, why is the negative there? The negative is there because we're looking at it as two regions of space, the system and the surroundings, right? So if you wanted to have surroundings over here, you would get rid of the negative. In other words, as energy goes into the surroundings, that increases the entropy change of that increases the entropy of the surroundings. But the issue is that we don't generally have values for this. We don't have those values. What we do have values are these. These are listed in Appendix 2. Because what we can do is we can use delta H of the system is the same as delta H of the reaction. Remember, the reaction is the system. Sum of the number of moles of the products times delta H of formation of the products minus number of moles of reactant times delta H of formation of the reactants, right? You've seen that before in previous course. So we look these values up in Appendix 2, calculate this, and then throw it into this equation, and that gives us delta S of the surroundings. Once you've got delta S of the surroundings, got that one too, we can now make our prediction about whether the process is spontaneous or not by calculating delta S of the universe. Kind of an interesting way of approaching it. Okay? So in other words, if the total entropy, the entropy of everything together during some process is positive, meaning it increases, the change in the entropy increases. Let's come back up to here. If this increases, the process is spontaneous. If it decreases, the process is not spontaneous. So in an explosion, the entropy of the system increases, but the entropy of the surroundings increases too. So if you have two positive values and you add them together, that's going to be positive and it would be spontaneous. But some processes are non-spontaneous, so the reverse of an explosion, right? In fact, we're kind of aware of that. In a sense, entropy it kind of makes sense intuitively, right? If you were to watch a film of an explosion going backwards, you would know there's something wrong, right? You know that doesn't happen. We don't have explosions going backwards. You would know that the video you're watching is going backwards. So what, in a sense, we have in our everyday experiences this idea that entropy and spontaneity are connected. When things become more disorganized, we experience that as a spontaneous process. Imagine if you were to take all of your nicely folded clothes and throw them all up in the air at one time. We know that the clock is moving forward if they all fall down randomly and disorganized. Entropy is increased, and that's a spontaneous process. On the other hand, if you then gather up all those disorganized clothes and throw them up in the air, to imagine them to land perfectly folded in piles, we know that wouldn't happen. That's a non-spontaneous process. So in a sense, chemical reactions are connected to this idea of order and disorder, which we call entropy. Disorder is entropy. And the direction in which a reaction goes is connected to what the statistical probability of something occurring is, right? The statistical probability of throwing up all these random clothes and having them land in piles. It's not impossible, it's not zero probability, but it's such a low value, it's just not a spontaneous process. Okay. So that's our strategy then, is to essentially calculate delta S of the universe. We'll modify that a little bit when we get to the next chapter. Now let's just look at an example. So the example your textbook lays out is the Haber process. 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to form 2 moles of ammonia gas, ammonia vapor. And we can measure delta H for this. Delta H for this reaction is minus 92.6 kilojoules per mole. Okay. Where did that number come from? Well, you could calculate it from the heat of formation data in Appendix 2. Okay. So let's calculate then delta S of the surroundings. Very simple. Delta S of the surroundings is, let me write this properly, is the negative delta H of the system, which is reaction, I guess, divided by T. So it depends on the temperature, right? So let's say our temperature is 298 Kelvin. Let's make that a point, because this data is for 298 Kelvin anyways. So let's figure out what the change in entropy of the surroundings is in this case. Well, it would be minus a minus 92.6. Now I'm going to go ahead, I'm going to go ahead and convert this to joules per mole for the delta H. So 92.6 times 10 to the 3. Remember, kilos 10 to the 3. So joules per mole. And then we're going to divide that by the temperature, 298 Kelvin. Okay? So let's take a look at what happens to the sign. Negative of a negative is positive. So this means that if energy flows out into the surroundings, the entropy change for the surroundings is positive, an increase in entropy. So let's do the calculation. 92.6 times 10 to the 3. So let's clear all this out. 92.6 times 10 to the 3 divided by 298. And you get 311. The units now would be joules per k mole, right? You got Kelvin here and you got moles. Those are the units of entropy, right? So the entropy change for the surroundings has increased. Now we could also look up the delta S of the system. Okay? And again, we learned how to do that in a previous section. You would look up in Appendix 2 or in whatever table you're looking at, you would look at those values up. Let's make sure everything's under standard conditions in these calculations. And if you do that, you'll find that it's negative 199 joules per k mole. Let's come back and evaluate that, right? We said earlier that if you have a larger number of moles of a gas and it becomes a smaller number, that would decrease the entropy. So that's why it's negative 199. is because 2 moles of ammonia vapor have less entropy than 4 moles of nitrogen and hydrogen together. So now, delta S of the universe would be the sum, right? You add the two together. You take your 311, and you add to that your negative 199, and you get 112. So essentially what has happened is you get a positive value, right? If it's positive, that means it's spontaneous. This is a spontaneous reaction. If we take nitrogen and hydrogen, we would expect it to form ammonia, even though, and this is an important point, it's often lost on students when they're studying this, we cannot determine whether a process is spontaneous merely by looking at delta S of the system. If we looked at this only, we would predict that it's a non-spontaneous process because it's a decrease in entropy. But it is spontaneous, and the reason it's spontaneous is because so much heat is released to the surroundings, it's so highly exothermic, that overcomes. There's an increase in entropy of the surroundings that's greater than the decrease in entropy of the system. Isn't that interesting? So in other words, if you have two regions of space, this is your system and this is your surroundings, if the process reduces the amount of entropy in the system, but it increases the entropy of the surroundings by more, then it's a spontaneous process, right? So if this negative 199 had been negative 399, then it would be non-spontaneous because it would be such a reduction of entropy in the system that would overcome the entropy change of the surroundings. And that's essentially our idea here. By the way, this equation here, I didn't mention it because I don't like to label things too much. This equation right here, where you're summing up the entropy changes, this is sometimes referred to as the second law of thermodynamics. Second law. Okay. Now, let's move on to one more topic associated with this idea of entropy. And that has to do with the idea of our statistical equation, which we talked about back in the first section. And let's look at limits. So let's suppose that we come up with some way, some like amazing refrigerator. And we take a solid. Remember, a solid's made out up of either atoms or molecules that are bound together tightly. Solids tend to have less disorder, less entropy than liquids or gases, certainly gases. So imagine we have this solid, and we're going to call it a perfect crystal. Now, when I say perfect crystal, what I mean is every atom is identical to the next. So there are no isotopes. It's not like it's carbon-13 and then the next atom next to it's carbon-12. They're all the same isotopes, so they all have exactly the same mass. They are arranged in perfect order, right? So they're right on top of each other. And we reduce the temperature to 0. So we're going to approach 0, not Celsius, but Kelvin. Now, remember for gases, we did this little calculation back in a previous course. The average kinetic energy is equal to 3 halves. If you have a collection of gas molecules, the average kinetic energy of those gas molecules is equal to 3 halves RT. What happens if you reduce the temperature to 0? Absolute 0, we call that, right? It's 0, right? The average kinetic energy becomes 0. So what we're going to claim here is that if you reduce the temperature of this perfect crystal to 0, there is no kinetic energy. So there's no vibrational energy, there's no rotational energy, there's no translational energy. Now, in fact, this is impossible, and quantum mechanics puts limits in terms of what would happen, but let's just assume that this ideal situation, that the temperature approaches 0 Kelvin, and there's no energy. We sucked all the energy out of this. We just have matter. If it's a perfect crystal, what we'll claim then is that the entropy of this crystal is going to approach 0 as well. Okay? So if the temperature approaches 0, the entropy approaches 0. And the significance of that is that when we talk about standard entropy values, which are listed in in Appendix 2. Okay. So for example, if I claim hydrogen has an entropy value of 131 joules per kmol, or oxygen gas has a value of 205 joules per kmol. How can we claim that we know the standard entropy values? How do we know that? Well, one way to do it is through an experiment. It's kind of interesting. What you do is, let me form a little graph here. Is you take advantage of the idea of this, that delta S for any process is the final entropy minus the initial entropy, right? So if I say that at 0 Kelvin, let's let S initial equal the entropy at 0 Kelvin. Well, based on our looking at this perfect crystal idea, that would be 0, right? At 0 Kelvin, a perfect crystal of some substance would have a value that's equal to 0. So if we allow that to be 0, then delta S is equal to S final. So all we need to do is look at how much the entropy changes, okay, as we put heat into it. And that will tell us S final with the assumption that S at 0 Kelvin is equal to 0. So that's a very clever approach that we can use to tabulate standard entropy values. But let me show you what happens essentially. If you measure entropy, I won't put units in, I'm just going to put S for entropy, for some substance, and you plot that as versus temperature, and we'll go ahead and put this in Kelvin. What you find is that if you're talking about a solid, the entropy increases linearly as you increase the temperature. Okay? So if you take a solid, right, so all these atoms are packed in together like a solid, and you measure what happens as the temperature increases, its entropy increases linearly. It's proportional to the temperature or the amount of heat that you're putting in. But then at some point it'll start to melt. And so now the entropy increases very rapidly as it melts. Temperature is not changing. Remember, when a substance is changing state, going from solid to liquid or liquid to gas or vice versa, the temperature doesn't change. But the entropy sure does, right? As something becomes a liquid, it's going to have more random motions. The molecules are now able to move around, so it's going to have more entropy. And then once that phase change is complete, once now it's a liquid, the entropy, again, as you increase the temperature, as you add heat as a liquid, now the entropy increases linearly again. Slope might be different than it was for the solid. Then at some point, you reach the point where it starts to boil, right? So this is where it's melting. But now at some point, it's going to start to boil. It's going to vaporize. Okay, so now we're talking about the molecules moving very far apart and moving faster, more kinetic energy, a broader distribution of entropies. The entropy increases quite a bit, right? So now, this is called vaporization. And eventually you reach a gas. Right, now we have a gas. Okay? So the entropy then can be looked at in terms of, and measured in terms of how we add heat. As we add heat and look at how the temperature is changing, we can figure out values of entropies that way. Okay? So there's a little intro into, by the way, this idea that the entropy of a perfect crystal at 0 Kelvin, sometimes that is referred to as the third law of thermodynamics. Third law. Okay, so the second law has to do with the idea of the sum of the entropies of the system and the surroundings is equal to the entropy of the universe, and if it's greater than 0, it's spontaneous. If it's less than 0, it's non-spontaneous. The third law is this idea of the perfect crystal, which is the entropy of a perfect crystal as the temperature approaches 0 will also approach 0 joules per k-mole. That is one definition. If you move on into physics and engineering courses, you'll see modified versions of that definition.